And in this video we are going to discuss the Leetcode problem, min cost to merge stones. I would say this is one of the harder DP questions on Leetcode, and it also took me some time to understand and get a hang of it. So let's see what the problem is. So you are given an array, and each element in the array represents a pile of stones, and array I represents the number of stones in ith pile. And what we have to do is we have to pick the k consecutive piles out of these piles, and we have to merge them, and the cost it takes to merge is the total number of stones in those k consecutive piles. So for example, let's say if these are the stones that we are given and k is 3, so we can see that the cost will depend on which we choose first to merge. For example, if we let's say we choose these 3 to merge, then the cost for these 3 would be 8 plus 1 9, and then we have 3 more left, then we merge these 3, so the cost will be 9 for the first merge, and then again to merge these would be 17. So this was the case 1. So case 2, let's say we merge these 3 first. In that case the cost would be 5 plus 1 6 plus 2 8 to merge these 3, and then we have to merge these 3, which would again take 17. And third option is that we merge these 3. So this was the first, this was the second, this was the third case, and if you merge these 3 first, then our cost to merge these 3 would be 3 plus 6 9, and then we have to merge these 3, that would be, so it's basically 9 plus 17, and minimum of these is this 17 plus 8, which would be 25. So the answer is 25 for this case. So yeah, so the answer clearly depends on which of these stones we choose to merge first, and it's a bit tricky now. So we will, for this problem, we will use the standard DP state transitions based on length of subarray we are considering. So this is a very standard state that we use in many DP questions, for example in the longest palindromic subsequence based on length of the subarray. So what I mean by that is that, so the our state is dpxy, where dpxy stores the minimum cost to merge stones for subarray indexed from ax to y, that is the subarray ax to ay, and we start with length to be 0, that is when y is equal to x, and we keep on increasing length slowly, so then y becomes x plus 1, y becomes x plus 2. So this is a standard technique that is used in many questions. So basically first we calculate the answer for single length elements, that is we calculate answer for, let's say this is the array, then we calculate the answer for 3 for 5 for 1 for 2 for 6, then we calculate the answer for 2 length subarrays. So we calculate for 3 5 for 5 1 for 1 2 for 2 6, then for 3 for 3 5 1 for 5 1 2 for 1 2 6, then for 4 3 5 1 2 5 1 2 6, and then for complete length array of 5. First we observe that to merge k consecutive stones each time into a single pile, how many piles we can you have? So if we have k piles, yeah, we can merge into all of them into one pile. Let's say if we have k plus k minus 1 piles. In that case, we can first merge, let's say, these k stones into one pile, and then we'll again have k stones and we can merge it into one pile. Similarly, if we have k plus k minus 1 plus k minus 1 stones, then we can merge this into one pile, then we can merge these k into one pile, then we can merge these k into one pile. So the thing is that, let's say if n is total number of piles, then if n minus 1 modulo k minus 1 is 0, only then we can get a valid answer. Otherwise if it's not 0, we return minus 1, because we can't merge k consecutive piles again and again to get a single pile. Start with length to be 0, which means that there is only one element in the subarray we are considering, and if length is less than k minus 1, which means we have less than k piles, we would say that dpxy is 0. So we don't need any cost to merge less than k piles. So since k is equal to 3, so the index is 0 to 4, 0 to 4, this represents x, this represents y, and dpxy stores the answer for x and y. So L is equal to 0 means this diagonal elements, and since k is equal to 3, so if L is less than 2, that is L is for L is equal to 0 and 1, we'll simply put 0 here. So basically there is no cost to merge two stones, there is no cost to merge a single stone. And the next case is when L is equal to k minus 1. So if we have exactly k stones, then we would simply sum all the stones in all those piles, and that would be our answer. So sum of array x to array y, that would be our dpxy. So in this case, for 0 to 2, sum of these three elements is 5 plus 3, 8 plus 1, 9. For these three, the sum of this 3 would be 3 plus 5, 8. Sum of these 3 would be 6 plus 1, 7 plus 2, 9. Now the tricky part is when L is greater than or equal to k. So in this case, we have to break our subarray at some point mid, where mid would be greater than or equals to x and mid would be less than y, and of all such mids, we'll pick that mid which will give us dp x to mid plus dp mid to x, mid plus 1 to y, to be minimum. So minimum of all such mid would be our dpxy. So now what does this expression here mean? This means that if we have array 3, 5, 1, 2, 6, and we are considering L is equal to 3, which means subarray of size 4. Let's say we are considering this, then we can break this at this point, or we can break this at this point, and that's it. So here mid would start from x, mid should be less than y, and mid would be increased every time by k minus 1. Cases that we break at this, then we have these two sub problems, and for this the answer would be 0, and for this the answer would be 9. And if we break at the other possibility, that is if we break at 3 and 5 1 2, then this would give us 0 and this would give us 8. So in one case we are getting 9 and in one case we are getting 8, and we'll take minimum of that, so this would be 8. This would be 8. Now let's consider subproblem from 1 to 4, which is this subproblem 1 to 4. So either we break at this, and these are our two cases. So for this the cost would be 0, and for this the cost would be 9. Or we break at this and this. So for this cost would be 8, and for this cost would be 0. So again, minimum of these two cases is 8. Now let's consider our final subproblem. So here we can break. So we have three options: 3 5 1 2 6, 3 5 1 2 6. Now we increase our mid by 2, so we can break here. So this subproblem and this subproblem, or then we increase our mid by 2, then so we would have to break at this, which is not a valid break because mid should be less than y, so we stop at, so we only have two cases. So for this problem this cost is 0, and for 1 to 4 in this table, oh this was also 8, so 1 to 4 is 8, and for this subproblem the cost is 9, and here the cost is 0. So for this subproblem the cost is 9, and so the minimum of these two cases is 8. But wait, 8 is not our answer, as we saw that the answer was 8. So as we saw earlier, the answer was 8, and then we have to merge this, so 17, 8 plus 17, so answer was 25. So this is the tricky part. If L modulo k minus 1 is 0, then we also add to our answer the sum from ax to ay. And why is that? This is because let's say we had 4 elements a1 to a4. Now the answer for these four elements, let's say I'll call it to be dp14, would contain the answer if we split here, and that would mean that we obtain 2 piles. That is the minimum number of piles we can obtain, a1, and by merging these piles, let's say b0, so we obtain 2 piles a1 comma b0. And another option is that we split here and then we obtain again 2 piles. Let's say this is b1 and a4, and hence dpxy basically stores the value to obtain min value to obtain minimum number of piles, and the number of piles can range from 1 to k minus 1, because if we had greater than k piles, we can merge any of those k into 1, and ultimately we'll be left with 1 to k minus 1 piles. That's why we said that if L is less than k minus 1, then we don't need to merge and dpxy0. So which means that if any of the split, example A4, if any of the split does not have sufficient number of piles, only one pile, then we don't merge, we keep it as it is, and we don't even add the cost of that. But on the contrary, if we had 5 piles, let's say if we had 5 piles, A4 and A5, and we have 3 options. So either we split here, then since we have 5 piles, we have already answer for 4 piles, and answer for 4 piles would give us a cost to merge 3 of these and keep one of these as it is without merging, and that could be any 3 of these. So any 3 consecutive of these, let's say that was this. So answer to the sub problem of size 4 would give us the cost to merge these 3, which would be, let's say, B0, and this would be kept as it is. This cost would not be counted, and this cost is not counted. But now since we have 5 elements, L is 4, we have to merge these also into a single pile, because we have to merge as much as we can. And to merge this, the cost would be A1 plus A2 plus B0, which would be same as A1 plus A2 plus A3 plus A4 plus A5. That's why if L modulo k minus 1 is 0, then we have to, in that case, the splits would generate ultimately k piles, will be left with k piles, and to merge all those k piles into a single pile, into one pile, we'd have to add the sum from AX to AY. So dpxy would contain an extra term, sum of AX to AY. So let's see one more example, a quick example. Let's say we had 7 elements. Let's say we had 7 elements: A1, A2, A3, A4, A5, A6, A7. And let's say we split here. Now we have multiple options to split: A1, A2, A3, A4, A1, A2, A3, A4, A5, A6, A7. So we can split here or we can split here. So in this case, what we are saying is that we'll keep A1 as it is, and this is just a problem of size 6. So out of these 6, we can merge 5 of them into one pile, and one would be as it is. So we can merge any 5 consecutive into one pile, and let's say these are these ones, and the cost to merge them is B0. So then we'll get A1, B0 and A7. So the answer for sub problem 6 would only contain the cost B0, the cost to get merge these 5 guys, but it will not include the cost to merge A1, B0 and A7. We have to add that by adding this sum from AX to AY. So this is the final merge cost. So in this case, this sub problem since it has only 3 elements, it will store the cost of merging this, which let's say b0, and this sub problem will contain cost of merging 3 of these, which can be any 3 of these. Let's say these 3, let's say b1, and then we'll get b0 a4 b1. So this cost is already, to obtain this b0 a4 a1 is covered by dp x to mid plus dp mid plus 1 to I. So this is the cost to obtain this, but to merge all of this together we have to add this extra cost, sum of ax to ay. And final case, if we merge at this step, then again this is a sub problem of size 5. So all this 5 would be merged into 1. So the cost which we will get, let's say b0, would be the cost to merge all of these into a single element, and a6 and a7, the cost of this sub array would be 0. What 0 means is that we are not merging them yet. We can't merge them. And now to merge all of these 3, so we have to add basically b0, the cost for this, plus 0, the cost for right subarray, and then we also have to add sum of ax to ay. And this term only comes when L modulo k minus 1 equals to 0. If L modulo k minus 1 was not 0, let's say if we only had, let's say, up to a6, let's say we only had up to a6, in that case we'd just kept the cost to be b0. We'd say that we are not merging b0 and a6 because we don't have sufficient number of piles, we don't have 3 piles, and we'll keep it as it is, and dp of 1 to 6 would be simply b0 in that case. Could be b0 or the other possibility if we split at some other point, but I hope you are getting my point now. So basically dpxy stores the cost to split the given subarray into minimum number of piles possible, and if L modulo k minus 1 equals to 0, then after the splits we will have k piles, and to merge all those k piles we have to add this extra term of sum of ax to ay. So for example, in this case we got 8 here from this case. The 8 shows that 8 is the cost of merging these 3 elements 5, 1, 2 and keeping 6 as it is, and then we have to add the cost of merging these 3 also, 17, to that, and finally we get answer 25. An interesting question that might come across your mind is, how are we deciding our splits? That why are we doing mid plus equals to k minus 1 and not mid plus plus? And why are we starting with mid equals to x? So these were few of the questions that came across my mind, and I thought spending some time in explaining that. Let's say we had only 4 elements, a1, a2, a3, a4, and let's say we allowed this mid plus plus, then our first split would be here, and this would give us an answer of keeping a1 as it is and merging these 3 into some element b0. And let's say we had made our split here. Now this is the problem, because we can't merge a1 and a2 into a single element, and so we'll keep it as it is and cost would be 0. We can't merge a3 and a4 because they are less than 3 elements, and we'll also keep them as it is and a3 and a4, and cost would be 0, and hence overall cost to obtain this a1, a2, a3, a4 would be 0, and our purpose is not solved. Basically we are not getting the minimum number of files. not getting min number of files. So to ensure that we get minimum number of files, we increase our mid by k minus 1, and let's see what does this ensure. This ensures that we, first of all, this ensures that we always have behind this bar, we can always merge all elements behind this bar into one element. So in this case, we already have one element, and then we can merge these three into one. Let's b0, and then we keep our slit to be here. Then we can merge these into one element. Let's say that's kind of b0, and then we have a4. We can keep it as it is, and let's say if we add more elements, a1, a2, a3, a4, a5, a6, a7, and let's say we split here, then again we know that we could merge these into a single element, and let's say b0, and we can keep a6 and a7 to be as it is. And now, since before this split we have only one element, let's say a star, only one element, and after split we can have at most k minus 1, because dpxy would store the cost of at most k minus 1 elements, because if that subproblem had greater than or equal to k elements, we could pick some of those k piles and merge them into one. And since dpxy always stores the cost to obtain the minimum number of piles, so the minimum number of piles cannot be greater than or equal to k. So this subproblem, the answer dp mid plus 1 to y, this would be the answer for at most k minus 1 piles, and hence if we only keep one pile before this bar, we can ensure that in the end dp x comma mid and dp mid plus 1 comma y, this expression would have answer for less than equal to k piles. Will always have answer for less than equal to k piles. And for the case when this has k piles, exactly k piles, then this is the case when basically our L modulo k minus 1 is 0, and we further add to our dp the sum from elements ax to ay. And I hope now this discussion has helped you to make things more clear. So this was quite the tricky part of this algorithm, and I hope now this is quite clear to you, and it will become more clear as we'll do the coding part. Let's see you in the code. Thank you. Hi, I know the discussion went quite lengthy, but the code is quite small. So we have the stones array, which stores the size of the piles. The size of the stones array is n, and if n minus k modulo k minus 1 is not 0, then we can no way merge these piles into a single pile. We create a cumulative sum array so that it can help to obtain the sum of all the elements between indices x and y in the stones array in order one time. So this code is typically the code for creating the cumulative sum array, and I think it's pretty clear. Now we initialize our DP array with all elements 0, and basically we have to start from L is equal to k minus 1. For L less than k minus 1, all the dpxy values should be 0, and we have already initialized our dp array to be 0. So we start with L is equal to k minus 1, and so we always maintain a distance between x and y to be L, and we start x to be 0, y to be x plus L. We keep on increasing x and y. So basically this keeps on filling the elements in a diagonal fashion, as we saw in the video. And if L is k minus 1, we have exactly k elements, then dpxy is simply the sum of all the elements from index x to index y. Else we initialize our dpxy to be infinity, and then we have to do splits. So mid is equal to x, mid should be less than y, and we increase the mid by value k minus 1, and we see that dpxy is minimum of dpxy and dpx mid plus dp mid plus 1 to y. So these are the subproblems which are of length smaller than the current length, and we already have the answers for these subproblems. And as we discussed, if L modulo k minus 1 is 0, then we have to add to our answer the sum of all the elements from x to y, because in that case we would have k piles, and this is the cost to merge those k piles. Finally, if dp 0 to n minus 1 is not equals to int max, that is, if we could reduce this dp 0 to n minus 1 during these steps, then we return dp 0 to n minus 1. Else we say that it is not possible to merge into a single pile, and we return minus 1. But since we had already returned minus 1 in this case here, I think this is not required. Any case, I hope now this problem is quite clear to you. Please share it with your friends if you like this video. Give a thumbs up, subscribe, and stay tuned, as more and more good content is coming soon. Thank you. Bye bye. Tata.